So here's what it looks like. And if you get the defalco paper, you'll see that what appears on the four ends of these two lines that are running side by side depends on what is at the ends of each one. And the worst case is if the driven line is an open circuit and so is the victim, which is what CMOS is. We don't have parallel terminations in CMOS. And if the victim line is quiet, that means this driver is at a 1 or a 0, and that looks, for our purposes, like a short circuit. So this end of the line would be shorted and that one would be driven, and these would be what the waveforms look like, where at this end you see it looks like you differentiated the signal. And the other end we see a much smaller waveform, and if we run long enough, the two waveforms look the same. That one and that one look the same. This is the stuff that drove the phone company crazy with those bundles of wires. So we're going to be worried about backward crosstalk because that's the one that gets big quick in a board. And so this is a qualitative curve showing you how the two kinds of crosstalk are different. The forward crosstalk grows much more rapidly than the backward does. And if you were to run parallel long enough, the signal would be the same in both wires. Backward crosstalk is very different. You know, it grows very, very quickly. And there comes a point where continuing to run longer does not result in more crosstalk. We sometimes call that saturation. There is only one place I know where this is beneficial. In the RF world, we exploit this, a thing called a directional coupler, where we take a sample of what's on the main line. In the digital world, we don't have any such nifty thing we can use this for.